Like this?
Okay, hello, good morning, good evening, good afternoon, everybody, wherever might be. It is my great pleasure and honor to welcome BORIS. He's normally from Northwestern, but now he is part of 5 people who are doing research in quintuples in Oberwolfach. And the title of his talk is Hello, BORIS. It's all yours.
Okay, go ahead.
You can start, BORIS.
Yes, can you hear me well?
Yeah, I can hear you fine.
Great, okay. Thank you very much for inviting me. It's a great pleasure. So I will be speaking or talking about what was an old idea from the 80s. Which is a modification, you can view it as a modification of Hochschild and Cyclic homology. It's due, I think, independently in the 80s, it was, the idea was of myself, of Jean-Louis Laudet, and of Crichton Ogle. But somehow, well, there was something done there, and sort of a new attempt now. So what is it? First of all, A, as usual, is an associative, possibly non-commutative ring. And let me go ahead and give the definition. And it will be a little bit naive definition. And then I will, unfortunately, I will have to make it a bit more complicated. And so normally, so somehow to show that it is modified, I will do it like this. It will be an abelian group as usual, generated by symbols like this, subject to relations. And there are 2 modifications. Modification number 1 is that I change the relation. The relation will be changed in the following way. So as usual, as we do tensor products, we leave all the arguments except the ith argument. We leave it the same, and the ith argument maybe, let me introduce this a little bit, maybe awkward notation. I just define I just change what happens here, and instead of the usual sum, I define it to be Here is the change. I have a new term, I kind of deformed it. So I just, starting from AI, I go cyclically, I multiply. So somewhere here there will be a 0, and then I reach the second value. I don't know, can you see it well? So here it is. Yes, and also I impose the relation that this particular thing is invertible. So that's part of the definition. Yeah, I am requiring it. Let's see. Okay, so how about what can you say about it? Just to give you an idea, first of all, the first standard product becomes the group of invertible elements with the multiplicative group, because and this is the correspondence. So of course, you know, if I have which is, of course, you know, and the requirement is that 1 minus this is invertible, so it's just tautologically they are the same. Yeah, well, I'm sorry, except I generalize, I'm sorry, I generate the abelian group by it, yeah? So it will be the abelianization. So if I go from A to matrices over A and do this, then I get K1. Okay. How K2 appears, I will tell you later. But let me now give you the definition. So usual formulas. And also the generous is, you know, absolutely same formula. So A0 or it could be and the generous is you just insert the unit. They work absolutely perfectly at the level of those tensor products. And also, this cyclic permutation, the formulas work perfectly. So you get a cyclic object in the category of abelian groups. And you can define Hochschild cyclic, negative cyclic, all sorts of this package. Okay, but this is maybe let me go right ahead and tell you that for various reasons that I will try to explain, it's a little bit naive. And unfortunately, I have to make it maybe more cumbersome, but more realistic. And the way is just to resolve the relation. And so at n, so what do I have? I have so instead of declaring that but basically what I said before, I declared that D1 is by definition D0 plus D2. And now if I want to keep it I would say that I don't impose relation, I kind of so in other words, I just pass to the nerve of this operation which is just the same as the classifying space of the multiplicative group. Yes, so instead of just abelianizing it and forgetting everything, I do the classifying space. Okay, now what to do at the other levels? So how to resolve this? It's same idea. So now I will have I will consider all such symbols, now this set of them, with the requirement that 1 minus A0, A1, blah, 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 then AI, whatever position, A plus 1, blah, 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 AN is invariable. Okay, so those are my, and I have two sorts of operations. I will just
Yeah, much better now.
yeah.
I'm a bit confused about your symbols. So you have this column only at one place, ith place, and everywhere else you just
Ith place and I arise from 0 to n, so it could be to n in any place. And also, maybe I should say that when I have this, so when m is who m equal 1, yeah. In
Yeah.
this case, I doesn't matter. So I just
Mhm.
for n equal 1, I doesn't matter. Okay, and basically, what name should I give it on C? Yeah. Maybe CL or whatever. I still have the vertical things. Sure. I mean, it's just, so should I give you maybe just an example, you know, so G0, correct? G0 multiplies those, so it will be just yeah, so when you see, you multiply neighbors in cyclic order, and if this is a column, okay, so it will be a column. Yeah. So this is how it works. And here you basically have the nerve of this, well, non-commutative operation, kind of ad hoc defined with respect to A. I mean, I guess the A in question are those two, and this defines a monoid. Okay, any questions?
I have a question.
Yeah.
Does it lead to a bisimplicial set?
It is a bisimplicial set, and moreover, it's cyclic times simplicial.
Okay, thank you.
So it's a cyclic objects in simplicial
Cyclic
sets. It's basically maybe with some very small modification. It's, yeah, so should I say that? So it's cyclic that way. And simplicial this way. It's basically cyclic objects in monoids, maybe with a little bit of a modification. And if you have such a thing, it gives you, so fixing those and require and require those to be invertible, you get a monoid. And it's kind of cyclic object in monoids, and you take the node. So it's just just an aside, maybe. Rather, I would say that also when m is equal to 0, and here I have, well, nothing. And again, I doesn't matter, and moreover, those doesn't matter, don't matter. It's just the base point. Here, I identify all of them. Okay, so this gives me this cyclic by and also maybe it's a good idea to replace A by matrices over A, as usual, you know, infinite but of finite order. Okay, so by the way, so probably the right definition is Hochschild. Also, well, the geometric realization, you know. Let me call it HCL. HCL. Okay, so why is it related to K theory? We saw it already a little bit for just to check that down. We saw it a little bit for K1. Now let us maybe go a little bit why this algebraic structure appears in K theory. This was the requirement that is invertible. And also maybe what notation will I use? Which I mean that it is on the zero index, or it could be it could be also the ice index. Maybe it's not a bad idea to fix this notation. And then, so what I'm going to show next is given a pair of elements whose one minus AB is inverted. Then we will construct a path in GL2 and we will discuss what a path is. So let me do that. So I start with the matrix 1 minus A minus B 1. Then I multiply it on the left by this matrix to get rid of that entry. Maybe let me do it. I mean, I do this first, but the way I drew it, I will be doing it all at once. So if I do Gaussian elimination this way, I will get 1 minus AB in this position. If I do Gaussian elimination the other way, I will get this. By the way, it follows that and also this one. Okay, so in what sense is it the path? First of all, if you have any topology of the ring whatsoever, then you do have a continuous path, correct? You have you do have a continuous path, and the t equals 0, you get and similarly you have okay. So if you don't have any topology, you basically have to impose some rudiments of topology, and you do it.
Sorry, what is gamma minus?
Pardon?
Gamma minus, what is gamma minus?
Gamma minus is the other order.
Uh-huh. Okay. Okay, thank you. Mhm.
Yeah. So, so what we do, we adjoin to the ring a formal parameter t. I mean, it could be polynomials, except you will get a little bit incorrect, I mean, different answer. And I will tell you in a second what it is. And there are two maps. Rather probably know it is better to denote it like this. And just like this. And then you can add two variables and then three. And so on. So in general, it's better. Better to do it in a more symmetric way. So you add n+1 variable and you impose one relation, and then, I mean, the obvious formulas make it a simplicial group, simplicial discrete group. So you mimic the definition of the singular complex. Yeah? If there were a topology and those were continuous maps, you would have a singular complex. Now, those brackets or braces, unfortunately, so one option is just two polynomials. And you get the definition of the Karoubi-Villamayor K-theory. Unfortunately, it doesn't always coincide, or is not always isomorphic to algebraic K-theory. And to make it so you just add them freely. You free product by the free algebra generated by those things, modular relations. And there is a theorem saying that what you get is the algebraic K-theory according to other definitions. Okay, and so you get really a path in the geometric realization. So in particular, maybe to make it of a closer format, you get a bisimplicial thing, and as an edge, I would say, these maps. And by universality, you clearly see that there exists a map, and it happens to be a homotopy equivalence. As to Karoubi-Villamayor, it goes here. Yeah, and also for topological algebras, it goes, you really replace it by a singular complex, so it goes to topological. Okay, and maybe I think it's clear, what I said was kind of clear, that when was I going to say? When, so what do we have? We have this is a point in the geometric realization, and that is path in the geometric realization. And also, as we all know, conjugation by a symmetric. I mean, there is another sort of universal path. I mean, roughly speaking, you know, permutation is a partial case of rotation. So, roughly speaking, you can say that it could be said more algebraically. You don't need those complex angles to do this. There is this universal path. So, when 1 minus, well, when AB is equal to BA, and 1 minus AB happens to be invertible, you get an element of pi 1 of this thing, of GL, which is pi 2 of GL, of BGL, which is K. And this is the well-known symbol of Dennis Stein from the 80s, I guess, maybe even earlier, maybe the 70s. Mike Stein was my colleague at Northwestern for many years, and it appeared in the works by Suslin and Wasserstein. Leonia Wasserstein was my colleague at Penn State for quite some years. Andrei Suslin was my colleague at Northwestern. Okay, so here it is, and you may ask, yeah, and it really does satisfy this kind of cyclic relation proven by them way back in the 70s, of course, not in the 80s. And you recognize, you know, it's like cyclic 1 cosine. So this, of course, you know, I think motivated me and Vode and Kraisanoglu back then. Maybe I don't, maybe we didn't have enough motivation, kind of extra pieces of motivation, maybe I will tell you later. And let me tell you why this is true, actually. So what do we have? We have here so let me let's have B and C. So you have two paths, and you just multiply them as matrices. Yeah, as I did here, as I did here. I also multiply them for every value of t. And same here, yeah. Okay. So I get a path between here and there. But this is equal to how well can you see it? And here you have maybe let me try to write it bigger. So you get another path. So if here I have, I would say, A times AC, here I have A comma B plus AC in my old notation. And there are two paths from the same thing to the same thing. So maybe so if you have in my old notation, if I have those two invertible matrices, then I have two paths between them. One is this, and another is this. Ah, yeah, I forgot to include that relation. I am sorry. Yeah, so I will do it in a second, but let's look at this first. And yes, they are homotopic. They are homotopic, and this proves the relation that I forgot to put here, But with basically this bilinearity, change by linearity. Here it is. So really those three, they say that there is a one cocycle condition. Okay, so this is geometric picture for moving bilinearities. Of the Danish science symbol. How about the Hochschild relation, the one, I mean, skew symmetricity is basically on the nose, it's manifestly kind of symmetric, skew symmetric. What about the Hochschild condition? And let me try to draw it here. Let me. Yeah, so the Hochschild condition, I start with a 3x3 matrix. Which is here. And try to do Gaussian elimination. In different ways. So if I can so this thing we recognize it is just a BCA, sorry. BCA, so this is A, comma, BC sitting in the indices 0 and 1. BC. A, B, C, yeah. Sitting in indices 0 and 1. And I think you get the idea. This will be A, B, comma, C sitting in the indices 0 and 2, and this will be whatever remains, I mean, B, comma, CA sitting in degree 1 and 2, and so you get a simplex, and yes, it is, it is it can be filled by a homology, and you get the Hochschild relation for the Danish science symbol. And also, it kind of makes clear what to expect. So conjecturally, this sort of considerations, I think you see the pattern. Conjecturally, you have the way. So on the one hand, you have this yeah, I'm sorry. So here I will have well, this is realization with respect to this thing, and then so this is kind of my cyclic homology, and it will go just to the realization of the base initial set. So conjecturally, there will be such a map, and again, this computes the KCR, the right hand side. But also note that this sits in here, and as an edge, at least when you replace A by, I am sorry, I mean, I have to say, make this is okay. Yeah. Then as an edge, it goes here, yeah, basically for what, for n equals 0 or something. And I think the universal property is satisfied. So you also have a map back. Yeah, this is true. I mean, it's the homotopy groups of this thing are, you know, pi1 is a billion and it acts trivially on pi-n's. So the universal property is satisfied, and there is a way back, a map back. So conjecturally, there are those maps. I have no idea whether to conjecture that they are mutually inverse or something else happens. I don't really know. Okay, maybe also I will tell you in a second, kind of believing that at least from left to right there is a map. There should be some consequences, and we will look at those consequences. They do they are true. But first, maybe I would also say, what's the relation with the Miller or Steinberg, yeah? Steinberg symbol? If you have two computing elements such that one minus AB is invertible, then you basically have two invertible elements. And you can take their Milner symbol. Stein. And it happens to be this thing. One checks this, it's a kind of fun computation, but also note that let us check the relation. So here we have the Hochschild. Here we have the Hochschild relation, which is one minus A times this thing is one minus AB, one minus AC. And here you get in additive notation we have, yeah. So you do recover the bilinearity of the Milner symbol, of the Steinberg symbol. Hochschild.
May I have a question?
Yeah.
Are you going to prove that for a field, your conjecture is satisfied?
No idea.
Aha. Even for a finite field like F2, for instance?
I haven't checked. No, I don't know. No. Yeah, so if you have maybe probably the easiest is I will do this in a second, but let me just so by linearity of the Steinberg symbol, you have this, and this is zero by the Steinberg relation. Okay, and allow me to erase this. So it will be, you know, and everything commutes, yeah. So again, by linearity, it's zero. Okay, good. Just an exercise, you know, to be sure what we are doing. Okay, so if we believe this, then what should be the consequences? So maybe let me. It's better like this. Well, and from here, you have two things. You have the Chern character to the negative cyclic homology, and let's say for simplicity that A is over rational Z and kind of nilpotent, pronilpotent. Let's say without unit, we just adjoin the unit, yeah, but should I say? So, what I would like to do, I would like to construct this. And in that one, I don't know, I can indicate it, or maybe, when A is it? Yeah, I think when A is commuted. No, I'm sorry, I cannot construct this. So this is conjectural, and this, unfortunately, for some reason, conjectural, but I can construct both. When A is commutative, and when I compose it, yeah, we were doing a lot of post-composing lately, and so with HKR also. When I post-compose it with HKR. And I think it's kind of instructive, and maybe not instructive, but intriguing, I'm not sure. Okay, so let me try it on. Oh, from Kyiv, Ukraine. Okay, wait. from your neighbors. Сейчас не могу перезвонить. Okay, so maybe let me this charm character. Let me tell you the leading term. It will be kind of the principal terms. Let me write.
Which one?
This is the charm character.
Okay.
So like the Danish trace map and is the same Danish. It would be, I think it would be literally this, yeah, or maybe. And this is in. This is in CLN, by the way. This is in CN. Okay, so yeah, there is this shift. Okay, and so I'm not sure, but when you so that's basically it. It is am I
Look, you see.
yeah, those logs, do I need those logs or not? I mean, maybe not, you know, at least. I mean, something like that involving differentials. I think I'm confused a little bit. I have to look into the formulas, but basically that's it. Let me rather go to the other one, to the goodwill regulator, so to speak, and let me draw the picture. I think it's intriguing.
May I have a question at this point?
Yeah.
About these differentials you resigned to write down. Isn't it somehow related to polylogarithms?
Yes, this is why, yeah, you will see them in a second. I mean, you didn't see them there, but the secondary Sherman character kind of goodwill, yeah. This is why I was, I was kind of more anxious to write this. So first of all, let me write the complex. So again, and again, maybe let me drop. I mean, I will always mean that I have the span of those, of the set of those. Yeah. So here I will have So once again, what I draw now is sort of kind of the Hochschild complex. Yeah, it will maybe let me denote it by well by C or by kind of impromptu. And so as usual, I will have. So this will be a kind of double. Yeah, the total of this. So I would say that the differential will be first of all kind of Hochschild B, and then the sum of those plus minus gi's. And then I will have, I think, in Ezra's notation, I will have U inverse times the so maybe let me draw it and then do some explanation. So maybe let me draw. We usually draw the cyclic complex. Here I have UB. So just same picture as usual, but let us just remember that now in this thing, those participate. And there are kind of two differentials. So it's a little bit, you know, maybe it's not the same situation, but we have seen this format when we are doing, I don't know, cyclic homology of a differential graded algebra. It's a little bit like that. Okay, so from this complex, yeah, and from this complex, I want to construct a map from the same, or rather, with the complex of the same format. And again, my algebra is commutative, and nilpotent basically, pro nilpotent or over K or over Q, yes. So here the differential is 0, and here is UD. So both are just standard formats for the cyclic homology. And I want to construct a map. And I will bring it back soon, but here is the map. So everything is, communication. Everything is nilpotent, so I can freely operate this Pauli logarithm. And now I want to say when I am, P terms deep, correct, in the P column number P, there, where should I go? I should go to yes, and here I do have those. Oops. Here, so the this column of the picture maps to that thing by the corresponding polylogarithm. Okay. Yeah, and put the same column. Basically, well, this one also probably fascinating term. So what happens to the what happens to those higher kind of things that we use to derive our relations? Answer that goes to the previous form. Yeah, no, and let me write it. And you will have log p plus 2, if I'm not mistaken. And let me double check. Yes, and here I have so where let me write it here. Let me give some ad hoc notation. It's probably, well, I understand that it's just to give you some flavor of what's going on, and maybe you will recognize what happens. So I just already defined maybe let me. Do I have a couple of minutes for? Yeah, perfect. And again, maybe completely, I measure how, those logarithms, how those multiple logarithms are not logarithms, how they do not respect the product. And let me just say that this thing appears at this value, and all the others are zero when the number of primes is greater than 2. All those numbers are zero. So I don't know, kind of looks fascinating to me. Oops. I don't see power.
Where's the three?
Oh, yeah, so I think hopefully you got some flavor, and I think it's a good time to stop.
Okay. So let's thank Boris.
Thank you.
Any further questions, Tomek?
Yes, I have a question
Mhm.
about cyclic homology
Yeah,
as a homology of the Lie algebra
yeah.
of associated with the associative algebra.
Mhm.
Is there some parallel between your construction? Is this isomorphism, well-known isomorphism, in a sense, infinitesimal form of what you are doing here?
Mhm. Oh, yeah, I don't know. No idea.
Okay.
Looks a tiny little bit like you pass from the Lie algebra to the group, but no idea actually.
And what was this question about his conjecture being true for the field? Can we go over it again?
Yeah, there's a relation between his symbols and Milnor symbols, defining K-theory for field. So up to the level of K2, everything
Agrees.
agrees, yes. So the question is, can you prove some Milnor isomorphism between K-theory written in terms of the symbols and algebraic K-theory? It would be nice to have at least this isomorphism for a two-element field.
Yeah, I am not sure if that helps you a lot.
It doesn't help.
Maybe, yeah. I mean, in general, yeah, kind of look at it and compare it to Bloch, Goncharov, I don't know, to some sort of complexes that appear there, and maybe modify this, modify that, and try to compare them. Yeah, but at the moment, I don't know much more than what I said.
Okay, thank you.
Tomek, any other questions? You are done.
No, I'm done.
Okay, anybody from Oberwolfach?
So I'm afraid we have to start going down for dinner. So questions will be later.
Okay, and anybody else on Zoom? No, Sasha? How about you? Adam?
No, I don't have any questions. Thank you.
Okay, it seems nobody else has a question, so in this case, let us thank Boris again for his talk.
Thank you very much.
Let me stop recording.